By now, those of you who have heard the first and second chapter of our Smart Meter School have heard me refer to the electrical utility power meter as the utility's cash register. But don't take my word for that. In a minute or two, listen to the words of Mr. Tom Towns, who was the chief of meter training at Westinghouse Electric Power Meter Group for over 25 years. But first, let's consider how a power meter works. The power company generates electrons and sends them down wires in a stream of electricity. When electricity travels through a wire, it generates a very small magnetic field which surrounds the wire in a ring pattern. In this case, I've drawn the wire in red. I show I, or current, traveling through the wire, and I show two outer blue rings representing the magnetic field. I'm also going to show an example based on a light bulb connected to power. The light bulb takes power, 120 volts, using a magnetic ammeter with a circular probe surrounding one of the incoming wires to the bulb. I now take a measurement, and I see that this bulb is drawing 1.2 amperes. 1.2 amperes, of course, at 120 volts equals 144 watts. 144 watts very closely approximates the rated wattage of the bulb, which is 150 watts. But is there any magnetic flux, any magnetic field surrounding the wire outside of the ring pattern? Let's check. When I hold the meter near the wire, but not surrounding the wire, there's zero magnetic field. I measure zero magnetic field near the wire. As another way to measure the magnetic field, I have here a compass, in this case an iPhone with a built-in compass feature, and I'm holding the iPhone literally next to the incoming power wires, and I notice when I hold the compass, light on, I turn the light off, we hold the compass, there's absolutely no change whatsoever. In other words, the wires are exhibiting no sign of a magnetic field, except to the extent that I measure the field surrounding the wire, again in the toroidal or ring pattern. The power meter measures the amount of power used per period time, and the utility uses that measurement to generate the customer's bill. We all know that. And, as we said in Chapter 1, the power meter measures the current, or amperage, and multiplies that quantity by voltage and integrates that over time. In our example, we see that there is no magnetic flux or magnetic field in front of the wires. Electrical wires travel throughout your home, and indeed in all buildings, without generating any magnetic interference. However, when we surround the wire with a circular magnetic sensor, as I showed a minute ago, we do see that we have current flowing through the wire. And again, the amount of current times voltage equals power. Power over time equals kilowatts, which is the unit the utility bills by. If I were to leave this light on as an example for 12 hours, it would cost me a little under 50 cents. In the United States, there are still somewhere in the area of 100 million old-fashioned power meters that make these measurements using magnetic coils, moving discs, gear trains, and mechanical dials. These meters have a large number of parts, and they use a lot of opposing magnetic fields. Over time, they become less and less accurate. Oftentimes, these meters are referred to as analog power meters. Some people believe that the analog power meter generates less magnetic interference than a modern electronic digital meter. However, the opposite is the case. Let's let Mr. Towns of Westinghouse explain the inner workings of an old-fashioned electromechanical meter. and later I'll return in another segment and explain the inner workings of an electronic digital meter, and we'll make the comparison. There are two things to keep in mind about the old-fashioned meters. One, they are old, and they have many, many moving parts, which require adjustment to maintain accuracy, and they wear out over time. Secondly, in a single-phase residential meter, there are 3 magnetic coils, 2 current coils, and 1 voltage coil. These coils produce magnetic fields and consume valuable power. Let's listen to Mr. Towns. Part 1, Section A, is a simple but detailed explanation of the power meter for non-technical people. Part 1, Section B, is a much more mathematically based lesson on the actual scientific principles of how the magnetic power meter works. Utilities are now moving rapidly to replace these old-fashioned electromechanical meters as a priority set forth by the federal government. Our purpose in posting and discussing this information is to provide scientifically accurate and correct information to consumers concerning the differences of the old-fashioned electromechanical power meter and the modern 21st century meters. This has become relevant given all the media attention focused on the new meters concerning health, security, and privacy issues. This segment is principally meant to address the issue of EMF or EMI, meaning electromagnetic force or electromagnetic interference. Our next segment addresses the communication radio frequency devices and the meter's internal switching power supplies, which have been targeted by folks recently claiming to be concerned with meter safety issues.
Components of a watt-hour meter. The principles of a watt-hour meter. What are they, and how do they play for us? You know, it's surprising about this meter. It's our cash register. It's very important to us. You know, this doggone thing contains 250 parts, about 350 labor operations. You know, it does a good job for us. You may ask, what in the world is a meter? What's it good for? Well, like we say, it is the cash register. It's that device which will measure the amount of energy that a load uses over a period of months. Now, you may not like the bill, but it does it well, and it does it accurately. Okay. Components that make up the meter and the theory of the operation and how they go together is important to us. And I want to impart to you this afternoon a little bit about how they work together. 250 parts and 350 labor operations. You say, gee, how do they make them? Well, gee, you also want to know we sell these things for about 30 bucks a piece, too. Just a very small amount, comparatively speaking, to what they were in the days of Mr. Schallenberger. You say, who? Mr. Schallenberger. He was the guy who came up with the original watt-hour meter. You know, it's nice to know that that guy has put a lot of thought into it, because his principles are still being used, and they're very sound. Let me tell you about some of them. I think they'll be interesting to you. I guess you already know there's at least 2 major components to the electrical part of the watt-hour meter. There's also a part called the disk shaft. You know, that thing that turns, the thing that goes around and around and around. Yeah, that's the baby, you know, it keeps racking up those kilowatt hours. And of course, there's other parts to it. There's a cover, you see the cover, and there's a base and all that. Part of those components. But let me talk about the parts that are internal, the components of the meter. And I want to show you these parts and show you how they fit in this meter. In fact, I want to show it to you sort of in king-size version. I have what they call a big meter behind me here. It's a very clever little thing that enables you to look at a part on a king-size basis. describing it to you. It has three supporting legs which holds up a lot of heavy components. Matter of fact, let's look at the first component this thing holds up. It's called the disc and shaft assembly. It's a king size. You said, gee, that is a pretty good sized disc, isn't it? Let me show you what it looks like in the real thing now out of a watt-hour meter to give you the comparison. Here it is out of a standard single-phase meter. It's almost identical in nature. It has markings on it, the top and on the bottom. It has a thing that the engineers call a worm gear. There's also one on this one. I'll tell you a little more about them later. And down on the bottom, there is a particular projection which you may say, what in the world is that? Well, that happens to be the bearings of the meter. This is what makes it run nice and smooth. We don't like to have friction in our meter at all. In fact, we go to a lot of trouble to get all that friction out of there. How do we do it? Well, let me explain it to you. This is a bearing. It's made from a particular material called barium ferrite. It's a sintered metal, and when you magnetize this thing, it becomes an excellent permanent magnet. We magnetize that material with a north pole around the top edge as I hold it in my hand, and a south pole around the bottom one. He said, well, so what? What do you do that for? Well, here's the why of it. Because we got to have this thing working with something. And what we have it working with is this little piece right here. Notice the similarity? They're both about the same diameter, a little bit different in shape, same basic color, same basic material actually. This one also has barium ferrite. And we also magnetize this one with the north pole around the top of it and the south pole around the bottom part of it. Okay? Now, when I put the thing together, we have two north poles hitting each other, and you can see the repelling action there. And if I do it quick, you see, now that thing just sort of floats on top of that. See how it floats? Actually, it has very, very little friction in there. Very little friction. We actually make another part that goes with the system, and it's called the rotation system. And this is the top bearing. It has a stainless steel pin, fits inside of a little bearing on the top, and it sits up in the air. And if I'm nimble-fingered enough, I can see that the thing will just sit here and rotate. This is pretty right in my hand. It's all because we use a bearing top and bottom which repel each other. They repel each other, so they float. Okay, now let me mount this thing over here in my system. I'll put the bottom bearing in. I come along and I put the top bearing in, right on top of it. And I fix it such that it's right in there. Let me raise it just a wee tad. I don't want it to drag, but you can see now it sits there and has practically no friction. It rotates very smoothly. Gives us a good system for doing what Mr. Schallenberger wanted to do. What did this guy Schallenberger tell us in the first place? Can you help me there? Well, I'm sure you'll come up with an answer. But the answer that I'm going to give you is this, that the principle of Mr. Schallenberger's meter started out with a hunk of iron around which he wound a bunch of little turns, a bunch of turns of very fine copper wire, okay, to which he put two terminals, and which he ultimately took those two terminals and applied a voltage which we call voltage of line, V sub L. Okay? Mr. Schallenberger says when you energize that coil of the many turns with a line voltage, you're going to have a current flow in that, and I'm going to call it I sub VC, I of the volt coil. Now, when that current flows, it does a marvelous thing for us, and it's part of Mr. Schallenberger's principle. It produces what's known as flux. I'm going to call that flux of the volt coil. Now you look at that and you say, hey, what does that thing do anyway? Well, it's only part of what we're going to see, and I want to show you the real life thing. First of all, I have to explain to you that I just can't hold this big thing up there. I got a mounting pad for it. Let me put it up here first for you. Okay. Now I have a mounting pad for what I'm going to show you. As the man says, maybe we better start out by showing you the thing that we started with. We take a spool. Here is a spool, which is made out of nylon, and we wrap around that spool a whole series of turns. Would you believe that on a 240 volt meter that there are 8,400 turns? 8,400 times around this baby, which means we got a lot of turns of very fine copper wire. In fact, it's almost the size of the hair on your head. Very, very small. But it has a capability when it's finally encapsulated, that is, when we take and put around it a coating, a nice hard coating which gives you good insulation and good protection against shock and damage. Now these coils make up what's known as the volt coil. You can start out with this, and those things make up what Mr. Schallenberger said he wanted. He said, I want you to take a stack of iron and wrap a coil around it. Okay? Now let me show you the iron that goes into that, show you how it's made up. How about you holding your coil up here for me? And I'll take this particular thing and I will put it right down to the middle of it. Now there's the iron that Mr. Schallenberger said he wanted. Here's the two terminals. And here's the part right here that joins up with it. So I have a complete iron circuit. And that's known as an electromagnet. An electromagnet. That's what I have on the board up here. Okay? Now, let me show you my king-size version of that device. Here is my king-size version. I guess somebody wants to say, how much does that doggone thing weigh? Well, it weighs about 10 pounds. That's what it weighs. It's a tough thing to handle, but it does a beautiful job for us in doing part of our demonstration. Now let me take and mount this baby where I told you I was going to protect myself by mounting this nice little piece of clear glass here. And I'm going to take couple bolts to secure it. This is going to support it fine for me. All right. Now, before I plug this thing in, though, I want to show one of those tools that a good meter man likes to have in his toolbox. You know, if you're a mechanic, you know, you'd have a jack and a hammer and a screwdriver and a pair of side cutters. Well, the meter people also have things they like to have. They want phantom loads. You know what those are. We'll talk about phantom loads in a minute. You want phantom loads, you want connectors, you want all types of things called standards, timing devices. Well, they also say you need what's known as vectors. And you said, oh, wait a minute. I heard a man talk about those one time. He scared me half to death. Well, don't be afraid of vectors. They're another one of those tools in your toolbox. In fact, I can represent this thing called voltage here with a vector. Hey, let me put a little point right here, which I'm going to start around, okay? And I guess I'll just give me some reference lines, all right? I'll just look it up here from a reference line. And this is about 90 degrees apart and so on, okay? Can you see those all right? You see these little lines here for reference, all right? And it needs to be here, here. All right, now I'm going to put on my little reference thing here something that will symbolize the voltage, just V sub L. Well, it looks like this right here. You said, well, Tom, why do you do it that way for? Well, it's just part of the system. In fact, can you believe this? Maybe this will make it seem a little easier to see. Let me just take and do a little artistic thing here called an eyeball. Can you believe that's an eyeball? Eyelashes. If you're looking right across here at the end of this vector, all right? Okay. Now, can you visualize that thing being tied down, anchored straight down? Can you believe that this thing is turning in a direction counterclockwise, run this way? In other words, can you visualize my arm? My arm's a vector, pointed right at that fella right there. Here's a place up here is called the anchor. And it starts rotating around. It rotated 90 degrees. Of course, my arm doesn't bend too easily. 180 degrees, 270 degrees, and back to home. That's one cycle, or 1 hertz, that we in engineering are beginning to talk about now. In fact, most systems now are 60 hertz. That is, it goes around 60 times a second. 60 times a second. But my eye has a capability, like a camera, like a high-speed camera, which will, like that, and it looks at it and stops it dead motion. It looks like this to it, and I'm going to put a title on it, V sub L, representing what I put on my volt coil, okay? That particular volt coil right there, and that voltage applied to it, causes that current to flow. Where is that current? You got a wild guess? Well, I'll tell you what. If you know much about this old stuff called electrical, when you have an iron circuit and a lot of turns around it, and you energize it with a voltage, the current that flows in that baby is going to be behind the voltage. Would you believe that it's almost 90 degrees behind it? Look at the board up here again on that eyeball. It's looking at this voltage and it goes around. If it instantaneously saw the voltage right there, the current that's talking about right here, that voltage coil, in relationship to that thing, is going to be right down here. Remember after this was 90 degrees? Well, it's going to be somewhat less than that. Right along here somewhere is where that current of the volt coil is. And this is a part of the reasons Mr. Schallenberger's theory works so well. He says, if you will take a voltage, apply it to a coil of many, many turns, there will be a current which will flow, which will produce a flux, which will cause rotation. In fact, voltage itself never produced an ounce of flux in its life. Only current produces flux, and it's in phase with it right here, okay? There is old phi sub volt coil, approximately 90 degrees behind the voltage which produced it. All right, set that aside in your mind for a minute, and let me take you a step further. Let me come over here and do something that looks like this. Let me show it to you in real life so you understand what I'm talking about. Here is the piece, okay? A little fella, looked like the letter C turned on its side, okay? It's not a very big piece, comparatively speaking, to that voltage coil, but the little rascal sits in there like this, and we stack a number of them together and put other things on them, and they finally come out looking like this. Like this one, and you'll notice that there are quite a number of these little laminations in there. Depending upon the design is what the thickness will be, but engineers decide that when they decide to build a certain meter. Now this happens to be the iron as used in the current circuit, okay? Take a look at those and pass them around. There's quite a number of them stacked up there. It gives you an idea about how that stack looks. Now to that stack, we're going to add what Mr. Schallenberger said would be the next thing in this circuit. As a matter of fact, he said, you take a hunk of iron, a lot of turns. Another hunk of iron with a small number of turns. Would you believe? Around here, in fact, on a modern single-phase meter, there's only 2 turns on there. 2 turns. You see that iron circuit right there? Here is the turns of wire, and it's, of course, a real heavy copper wire. You say, well, what the heck you make it so big for? Well, that thing has to be able to handle quite a lot of current. Basically, in the industry today, there are three types of meters. There's a 30 amp meter, which will handle 200 amperes. There's a 15 amp meter, which will handle 100 amperes. And there's a 2.5 amp meter, which will handle 20 amperes. And we call these things class 200, class 100, and class 20, respectively. Let me just make a note of it on the board up here so you see it, okay? The first one is the one that will handle 200 amperes, and we call that the class 200. And of course, that is the 30 amp meter. 30 amp, 200 amperes capacity, or class 200. The 15 amp meter will handle 100 amperes, and it's also called the class 100 meter. The 2.5 ampere meter will handle 20 amperes, called the class 20. Let's review the numbers we just placed on the board. In this column, we have test amperes, TA, test amperes. We're talking about a meter with a test amperes of 30. That is, it is capable of handling 200 amperes continuously. It's otherwise known as a class 200 meter. Now, there are two other types besides the 30 amp test ampere type, the TA15 and the TA2.5, which will carry 100 amperes, or class 100, or 2.5 will carry 20 amperes, or called a class 20 meter. Okay? This 30 amperes that we're talking about right here is the one that has the two turns on it. In fact, it's an interesting phenomenon. Depending on which meter you're looking at, it doesn't make any difference really, because all of them are the same. How many amperes would you guess, test amperes would you guess, each meter has? How about ampere turns? How about any of those class numbers? Aha, those are interesting. In fact, all meters, whether they're GE meters, Westinghouse meters, Duncan meters, or Sangamo, all of them have 60 ampere turns. You say, well, what in the world is an ampere turn? Remember I said this was a 30 amp meter? If I take and divide 30 into the 60, 30 amps now, into 60 ampere turns, what do I have? Well, 30 goes into 60 two times, and the A's cancel out, so I have 2 turns. Hey, how many turns do I have down here on this 30 amp meter? I got 2. Now, let me show you something over here from the side of the table. I brought one in here just for the heck of it. You can almost look at them and you say, hey, I know what that is. I've already showed you the 30 ampere with the 2 turns. And if I showed you this one right here, which has 4 turns, you'd tell me right off the bat, hey, that's got to be a 15 ampere. 4 turns times 15 amps gives you 60 ampere turns. Now, if I showed you this one, you would look at it and say, hey, I know what that is. Well, that, of course, is a 2.5 ampere meter. And if you took all the turns off this little rascal and pulled them off, you'd find that there are 24 turns on here. 24 turns times 2.5 amperes comes up to be 60 ampere turns. So it doesn't make any difference whose meter you're looking at. It doesn't make any difference to how many turns it has on here. All of them are 60 ampere turn meters. Every last one of them. Okay? Now let's transpose from the little real things that were to my big meter again. Okay? The big meter, of course, uses very large wire. And this happens to be a singular coil, that is at 2 turns, but a single coil, which I'm going to use in an iron circuit that looks like this. Here is the iron circuit right through here. To turn the other side, I've got a way to hold that current coil. Let me take the stack and place it over here in the meter in its proper relationship. Okay. Now, the current coil that I'm going to place in there, I place it around the stack and I tighten down the connections. Okay? What I am going to do is to circulate through here a current. You say, well, what in the world are you going to do with that current? Well, let's go back to the blackboard for just a minute and pick up the current in relationship to what Mr. Schallenberger said. At the risk of feeling that I am repeating a lot, let me quickly go over it. Mr. Schallenberger says if you take a iron circuit with a lot of turns, apply voltage to it, a current is going to flow and a flux is going to be produced. Mr. Schallenberger also said if you'll take a current and run through a very low number of turns, only 2 in the case of a 30 amp meter, or 4 in the case of a 15 amp meter, or 24 in case of a instrument transformer type meter, and I place that iron circuit in vicinity of the voltage coil, and I put a load out here. Let's put a little box out there. I don't care what the load is. Maybe it's a light bulb, you know. Could be a small motor. Could be any type of load. Okay? I'm going to take that load and I'm going to tie it to one side of where my voltage was tied, okay? The other side of it, remember that line starts right here, I'm going to tie to the other one, okay? In other words, all I have done is to put a voltage on this load, and except now the current's going to flow through these current coils. Now, if this load right here is resistive, that is, if it's like a light bulb, where is it going to be up here on my magic little thing called a vector diagram? Well, just tell you, if this is the line voltage, and that's a resistive load, the current's going to be right here. In other words, when that old eye over there looks over toward this thing where it's anchored and sees it rotating 60 times a second, the current that's in there is going to be right in phase. That's what the engineer calls it. In phase. It's flowing right with it. Right with it. That current, I sub L, in other words, that load current that you got right here, that current is produced by this load or caused by this load. That's going to flow and it's going to be in phase with the voltage. Now, when that current goes through these turns, it's going to produce another flux. Let me clean up the diagram a little bit so it makes a little more sense, okay? Let me just take out this part right here so that it's not so confusing. Right in here, in this iron circuit, is going to be a flux produced also. And I'm going to call that the flux of the load. This current right here is what produced it. Would you believe that the current produces flux? Therefore, the flux would be right here. This right here would be the flux. Phi sub load. Here's where the beauty of Mr. Schallenberger's whole experiment that we use today comes into place. He said, if the flux of the load and the flux of the volt coil are displaced 90 electrical degrees, you're going to induce into this thing called a disk. And I'm going to quickly put this in here and show it to you in the real thing. The disk shaft assembly which is mounted on bearings, remember, is right between that. Now follow me over here and notice that I have my Vogt coil here, and I have that disc shaft assembly rotating right there, and I've got this current coil right here, okay? Now let me just place the current iron and current coils in proper relationship. I'll just move it back underneath the disc shaft. Now all I have to do is connect these things up. I'm going to do them one step at a time and let you help me out in what you guess what's going to happen, okay? First of all, back here in the back side, I have a source of voltage. Now, I'm going to hook my little service convenience outlet here up to it, okay? We'll hook it up right there. And then I'm going to take, remember I started out by saying I had a regular plug? Okay, I'm going to plug that baby in. Now, in this, we ought to be producing flux. How can you tell that anyway? You have any idea? Well, I carry a nice little thing with me called a hacksaw blade. Just a plain old hacksaw blade. And that little rascal's made of steel. And all I got to do is sort of hang it up in there. And, you know, can you hear that? You don't hear that buzzing like a rattlesnake? Well, that's a lot of flux being produced with that rascal, see? Let me go back to my diagram now. Here it is. It's right here. That's what's causing the noise. That flux right there. It's produced by the voltage of the line being tied to the Vogt coil, which is this little representation here. That causes a current to flow. This current right here. And this current is what produced that flux. Okay? So now we have a flux produced by the Vogt coil. It's all by itself, though. It does not cause any rotation of the disc. Mr. Schallenberger says it takes two things. It takes the flux of the Vogt coil and the flux of the current coil to produce that rotation. Well, let's talk about current produced by the coil. Let me just take this off here so we get rid of our noise. And we'll just go over here and look at a little device sitting on the table. By the way, this thing gets a little hot, so I'm going to unplug it just for the temporary, okay? Back over here, I have what's called a phantom load. You said, boy, the last time I saw the Phantom, he was in the movie somewhere. Yeah, well, that's probably true. This is sort of the same sort of a setup. It's a phantom thing because what we want to do is put a load on this baby without producing a lot of heat. Let me tell you how it works very, very quickly. It's not in the world but a transformer. It has a primary, which has 120 volts tied to it, and it has a secondary. And it has taps on it with resistors and so on. And we then open that up and place it in our current coils. What we do is reduce 120 volts down to about 12 volts, and we effectively put little resistors in here and we short them out and make a current, whatever current we want to flow. Little detail, but it helps you in understanding we're going to produce a current in this little black box right here that's going to flow through these current coils. Now let me show you how I'm going to hook that baby up. I've got leads on it, nothing in the world but alligator clips. And these little devices I'm just going to take and hook directly to the terminals. Like number one, a little closer, and number two. This particular secondary is flowing right through here. Back to my little diagram over here, what I have done is to hook one lead to that resistor and one to that one. And of course this one right here is going to be my current coil. I can represent that current coil very easily just by saying, hey, I got a couple of turns which I have around an iron circuit, okay? That current is going to flow through this and produce a flux. Let me turn this baby on. This thing is sitting on about 30 amps, and I turn that current on, and if I can feel the wire, yes, I can see a little something flowing through there. And I also want to turn on my volt coil. Would you hazard a guess is what's going to happen? What's going to happen? Would you think you're going to get rotation? You would? Which way do you think it's going to turn? Right to left or left to right? Well, you know, it's always fun to just go ahead and plug it in and see what happens. Uh-oh, the thing is turning right to left. Now, what do you guess I've done? Well, I have wired this baby up backwards on purpose. And my whole purpose in doing this is to show you that it's very important that the relationship between the units as we wind them are important, because we always want our meters to turn left to right. That's the way all American meters are set up. That's the way we want to do it. You say, how can I do that? Well, it's very simple. All I got to do is to change the current coils. First of all, I'll disconnect the voltage. Boy, you see how fast that thing's going? Actually, it is turning up close to 1,500 revolutions per minute. What have I got here, just as you see it now? Well, I tell you what I've got. It's a motor. Particular type of motor, but what we have is a flux produced by a volt coil, a flux produced by a current coil, and it's producing rotation, but actually it's a motor. Okay. Let me put on the proper connector. Let me turn off the current, disconnect the alligator plugs. Okay. I'll unfasten them. Extract out that coil, which is a bad one, and get a good one over here, which is almost the same, but it's a little different in shape. Actually, it turns up a little different. Let's see what happens when I place it on the other side. Okay. Down in that connection. I tighten this up good and tight. This one up good and tight. I put my alligator clips back on it. And I take and I put my meter back up inside the way it should be. Okay. And I take my volt coil and plug it in. And I turn my current on. And what do you guess is going to happen? Well, it should turn the other way, shouldn't it? Let's see what happens. Uh-oh. You see what that disc is doing? You see what it's doing? Takes a while for it to react. That baby's slowing down, down, and down. And finally, the torque that's being produced by the interaction between the volt coil and the current coil is in the proper direction. It reverses, and now it's turning in the proper direction. The proper direction, but not at the proper speed. How'd you like to have a meter that's sitting out there turning up like that? Boy, wouldn't that rack up the kilowatt hours for you? That would get you a bill from our friendly power company that would make your head sort of dance. And you can't afford that, can you? Well, how am I going to turn it from that motor into a meter? Somebody know the answer to that? Well, let me just say this. It's a pretty complicated answer, but suffice to say, what we do is we add drag to it. How would you guess I add drag? Well, I'll tell you how it's done. It's done with a permanent magnet. Here's my king-size version of the magnet. It's nothing in the world but a piece of material which has a magnetic field on a permanent basis. Now let me just show you the real thing from a real meter. It looks just like this. A little bitty fella. It's C-shaped, just enough hole placed in it that the disc will turn through it. But when we magnetize that, and we put the north pole here and the south pole here, there's a magnetic field that flows between that, and when we put our disc shaft in there, it will cause something marvelous to happen. Let me show you what happens when I take the time to place this on my meter as it turns. Notice now that I have gotten up to full speed over here, But to keep the thing a little bit cool, I'm going to disconnect it for a minute while I place this little device on my meter. To help in being able to see it, let me just rotate this whole carriage around a wee tad, so that it's around here on the back side, if you will. Okay? Now, can you see that a little bit better? Let me just take and place this little thing right on here, so that it's going to effectively move in this direction. Let me take a piece of hardware. This is going to support it for me. I've got two of them to put on here. Okay. Now, I'm going to get down on my hands and knees so I can see. I know that you're going to be able to see all right. But what I want this thing to do, this disc shaft, to go right through the throat of that. Okay? So it's a little bit low, so what I'm going to do is I'm going to raise it a little bit. Just a wee bit. Now, if this is working like it's supposed to do, when I place this magnet right on the edge, then that disc is immediately going to start to slow down. Can you see that it did? In fact, can you believe right now it stopped? In fact, that's what you'd want in your meter. When you don't have any load on that rascal, you want it to stop, don't you? Otherwise, you'd have what's known as a creeping meter. And nobody loves a creeping meter. We choose the strength of this thing so that it does present a drag proportional to the load which is flowing through it. Okay, let me get off my knees and turn my meter back around in this direction. I'm going to again place my current in the meter, and I'm going to place my voltage on the meter, and you can see that the meter is immediately starting up and moving left to right as it's supposed to do. But notice also it's moving exceedingly slow compared to a minute ago where the permanent magnet was not in place. Okay? This is an adjustment, really, and that is going to be another subject which I'll cover a little bit later, called the full load adjustment. What I want to do now is to go back to the blackboard, and I want to review with you what we have gone over so far. Let me take my piece of chalk here in hand. Remember, I said I had a volt coil which I hooked to the line voltage. A current was drawn from that, and that particular thing produced a flux. The current coil has a current flowing through it which is caused by a load which we apply to it. That current in itself produced a flux. It's this flux right here we produced, and this one. Mr. Schallenberger says if you will take this one and cause them to get into that nice little stripe which is known as the disc shaft assembly, and of course there is a shaft bearing. Here's the top bearing, that pin bearing, and it goes on down here, and we got a bottom bearing which is nothing in the world but a piece of barium ferrite that we described at the very start, and that disc rotates. And when these two fluxes get together, something happens inside of this little piece called a disc shaft. Would you believe that there's things in there called eddy currents? They don't particularly like the position which they normally get into because some of them are going one way, some are going another way. And they sort of combat each other somewhat, but eventually they will produce a reaction to an action they started out with, and will produce torque and also cause the disc to start turning. If I let it keep on turning, then we're going to have a motor. But what I basically do, and I'm going to erase my eye over here and show you where it goes. here is that disc shaft right here, and I place right in this position. Around here, I place that permanent magnet. It has a north and south pole, and the lines of flux go right between that magnet. And when that disc is turning, and this flux is here, there is a retarding motion that takes effect, and that will slow the meter down. You say, why is that important? Well, the big question is, let me just delve a little bit. If you were a man with a lot of money and decided you wanted to build meters, and you built a nice plant, you spent probably several $1 million on tools, and then you hired some nice engineers who knew what the heck they were doing, and you say, I want to build a meter. Okay? And those guys go to work. What do you think the very first thing they're going to decide when they start designing that first meter? You want to guess on that one? Well, I'll tell you what they decide on. They want to decide how fast they want that meter to run. That's the very first thing they'll decide. Because that is the key to a lot of other equations, which we're going to cover a little bit later. The speed of the meter is the very first thing. To adjust the speed, we coordinate between the volt coil number of turns, the number of ampere turns on the current circuit, how many revolutions per minute that device is going to operate. Would you believe that in the design that I showed you from the very outset, the very first meter that I showed you, that meter is designed to turn at 1,000 revolutions per hour when you put the nameplate voltage on it and the nameplate current flowing through the current coils. 1,000 revolutions per hour, or 16 2/3 revolutions per minute. And the way we adjust that is with this thing right here called the permanent magnet. The way we adjust it is very simple. We take a screw, a steel screw, and I'll represent it this way, and it looks something like this with a slot in it for using a screwdriver on it. Okay? And that screw is something that is held, so to speak, permanently in a holder. And when we turn the screw in and it gets up close to that south pole, what do you think is going to happen? Well, part of the magnetic field is going to be diverted. And when it's diverted, there's not going to be as much between the pole pieces. It won't be as concentrated. So if it's being robbed off, so to speak, and not as much in the air gap, the meter is going to speed up. Conversely, if we take our screwdriver and back the screw out in this direction, back it away from that, it's not as effective. Therefore, there's more concentration of flux, and therefore the meter is going to slow down. So moving the screw in this direction slows it down. Moving the screw in this way makes it go faster. A very simple little thing called the full load adjuster. Okay. Let me take time to erase the blackboard.